Alrighty, so page 138, try these A. These two are from Try These A. The one labeled D here is not. It's one that came off the internet. First thing we should check, it's in proper form, descending powers. There is no greatest common factor to pull off, so we'll just go ahead and count the number of sign changes. Well, it went from positive to negative, and then it went from negative to positive, and then it stayed positive. So there were two separate sign changes. So this would mean there are two positive roots, or there could be 0 positive roots. We don't know which. But there are either no positive real roots or there are 2 of them. We're not going to get 1, we're not going to get 5. Those are 2 choices. Then to check out the negative roots, that's where we put a negative x in and count the signs. So we put a negative x in and cube it. A negative number cubed is going to come out negative. Then, and if we put a negative x in here and square it, that's going to make it positive. Times a negative 4, this will still be a negative 4x squared. We put a negative x in here, this x will become negative. And the positive 5 is going to stay positive 5. Once again, we just count the changes. Well, negative to negative, that stays. To negative, that stays. But then a negative to a positive, that's a change. So we do have one change for the negative values. That means there could be one negative real root if there were 2 positive roots. And we're not going to subtract any 2's from this. There could be 0 positives and still 1 negative. Somehow, there's going to be a negative real root here. There will be a negative x value on the x-axis. Now this was originally a cubic, degree 3. So if we had 2 positive real roots and 1 negative real root, there wouldn't be any imaginary ones. But if we had no positive real roots and 1 negative one, there would have to be 1 pair of imaginary numbers out there, because the thing has to have 3 roots, even if some of them are imaginary. Okay, this one looks pretty interesting. Wow. Same procedure though. It can have 5 total roots. That's the degree. And we're going to count the positive ones just by counting the changes. Well, it's positive, and it stays positive, and it stays positive. And then right here, it changes from positive to negative. And then it stays negative. And then it stays negative. If I did that right, one change here, positive to negative, and then it was negative thereafter. So there is one possible positive real root. And we won't have to step that down by 2, because you can. Now to find out how many negative roots, we'll put a negative x in wherever there was an x. So when you take the 5th power and a negative number, you're going to get negative x to the 5th. When you take the 4th power, you're going to get a positive answer times a positive 9. This is going to still be positive. You put a negative x in and cube it, you get a negative answer. So this would be negative 16, x to the 3rd. Negative x in and square it, becomes positive. Being multiplied by a negative 60, this would still be if we put a negative x in here and multiply it by a negative 224, we're going to get a positive 224x. And then we count the sign, the changes. Well, it went from negative to positive. One change. Went from positive to negative. Two changes. Stayed negative. Then it went from negative to positive. That's a third change. And then from positive to negative. That's a fourth change. So there could be 4 negative real roots. Or there could be 2 negative real roots. Or there could be 0 negative real roots. In each case, there could be 1 positive root. Now this thing was degree 5. Well, so if we have 1 positive root and 4 negative roots, that would take care of it. There would be no imaginaries. If we had 1 positive and only 2 negative, that'd only be 3 roots. We need 5 roots. There would have to be 2 imaginaries. If we had only 1 positive root, no negatives at all, we would need 4 imaginaries, 2 pairs of imaginary roots. Usually we're only worried about the real roots for right now. Okay, D was not out of the textbook. Just made it up. And I didn't put a thing on it here. That was my fault. So I'm just going to call this K of X. And it is in descending powers. It's missing a place here or 2, which is okay. But it has a greatest common factor. And we need to pull that out first. So K of X is X times 2x to the third minus 3x squared plus 1. And we already know that x equals 0 is a root. We have one of our 4 roots already. So we're only going to use the part in the parentheses here. We already know this is a root. It's not a positive root, it's not a negative root. But it is a real number and it is a root. So I'm just going to call this K sub 2. Equals the part in the parentheses. And if we count the changes, it went from positive to negative, and then it's gone from negative to positive. So there are 2 changes. That means there are 2 possible positive real roots, or there are 0 possible real roots. To find how many negative roots, we're going to put a negative x in. See what happens. So when you cube a negative number, you're going to get a negative times 2. That's going to be a negative 2x cubed. When you square a negative, it becomes positive, times negative 3. That's going to be negative 3x squared. And the plus 1 stays plus 1. And we count the sign changes. So we have negative stays negative, and then this negative becomes a positive. We have 1 sign change. So there could be 1 negative root. And that's all. If there are 2 positive roots, there's going to be 1 negative. If there are no positive roots, there's going to be 1 negative. And we already have that x equals 0 is a root. So the original equation was 4th degree. We have 1 root already. And then if we have one negative root and two positive roots, that would be all four roots, and there wouldn't be any imaginaries. But if we didn't have any positive roots, we just have one negative root and this 0 root, that's only two roots. We need four. There'd have to be a pair of imaginary numbers as roots. So it's not hard, and we can use it in conjunction with the other tools we've got to solve polynomials, which is what we're going to do next. But not until you would please do a little practice. So would you please look on page 100.